But there is a small challenge. I just want to caution that this trip will only apply for those who have registered for this unit or whichever unit for both units. And this applies also to Caroline's unit. So I hope everyone has registered for all the units that are supposed to be offered this semester. Is that so?
Yes.
Yes.
Yeah, because what the admin is doing is just checking on those who have registered, and they will only be able to facilitate those ones. We cannot just send a blind list of students that I'm expecting, because I do not know who have registered, who has not registered. So it's up to you to ensure that you have registered for that unit, for all the units, because that's what they will use to generate the list. And so if you have not registered, it will be unfortunate that you may not be facilitated to go for the field trip. So make sure, inform your colleagues that they should make sure that is the registration deadline already gone?
Yes, it's gone.
Okay. All right, then. It was just by the way, because we were trying to process that, and I was told the list that we cannot send a list because you guys are aware, and therefore we can only use a list that is automatically generated from your registration. Well, I think those are the two main announcements I wanted to make. Let us now embark on our unit, which is restoration of coastal and marine ecosystem. I think we parted ways when we were discussing about what the blue carbon is and the importance, or rather the relevance of coastal and marine ecosystem in relation to climate change mitigation. And I think we parted where I was trying to reiterate the importance of this coastal and marine ecosystem with regards to climate change mitigation. And I mentioned that coastal and marine ecosystems are regarded very highly when it comes to climate change mitigation. And in that regard, we have what we refer as the blue carbon, and we say that carbon, basically the carbon that is usually stored in these three major known coastal and marine ecosystem. Among them, the mangroves, tidal marshes, and the seagrass meadows. These three ecosystems, we say, are very, very critical when it comes to climate change mitigation because of their potential in storing carbon, or rather, if you will, in sequestering CO2. And we say that these ecosystems store carbon in various compartments. Among them, above ground biomass, we have the below ground biomass, we have the necromass, if you will, or dead biomass that is left in the compartment undegraded, and therefore it still plays a very important role when it comes to sequestration of carbon. But most importantly, the compartment that is usually very core when it comes to the storage of the carbon is the soil. And therefore, in relation to restoration of either of these three ecosystems is very, very critical. And most importantly to us at Western Indian Ocean, mangrove, the seagrass ecosystems therefore play a very important role when it comes to climate change mitigation. And therefore, that's why there is so much effort, there is so much focus on trying to restore these critical ecosystems in as far as these other ecosystems are also being restored or being restored. So, and therefore the question that I asked at some point is why are coastal and marine ecosystem very important in as far as climate change mitigation is concerned? And I mentioned to you that these key ecosystems, particularly mangrove ecosystems and the seagrass ecosystem, have very high rate of carbon sequestration and storage per unit area. And that is very, very important, because what this basically means is that in as much as these ecosystems are very small in terms of the area extent as compared to other important ecosystems, such as the tropical rainforest, the temperate rainforest, and the like, when it comes to the sequestration of carbon, and when it comes to restoration of those ecosystems, there is the potential, or rather the potential of coastal and marine ecosystem is very, very important because of the high rate of carbon sequestration potential that they have. So when you look at the sequestration rate of various ecosystems around the globe, and we compare them with our coastal and marine ecosystem. For example, when you compare the mangrove ecosystem vis-a-vis tropical rainforest, or if you will, boreal forest or temperate forest, what you will notice is that this particular ecosystem has got very high potential for sequestering carbon. And therefore, when we destroy a hectare of mangroves, its damage in as far as carbon sequestration is concerned is very, very high as compared to a tropical rainforest. And so is the tidal marshes and the seagrass meadows. And therefore, that's why there is so much focus on trying to protect these critical coastal and marine ecosystems because of their potential to store carbon. So in terms of the quantity of amount of carbon that they store, they are known to store up to 5 times more than most temperate and tropical rainforests. And therefore, that basically shows how important these 3 ecosystems are in as far as climate change or carbon sequestration is concerned. And the one thing that I have tried to underscore is the importance of the sediment compartment of these 3 ecosystems. When you look at these 3 ecosystems virtually, they may look like they are just simple ecosystems, and therefore many a times you may wonder why they are so much. There is so much attention around these 3 ecosystems. But one very important thing that I keep underscoring is that they have very high reach sediment compartment that stores a lot of carbon, and therefore there is very high turnover, particularly of the above ground compartment, and especially the seagrass ecosystem and the salt marshes. The seagrass here and the salt marshes, they have very high turnover rate, and therefore, when you look at the ecology of these 3 ecosystems, if you remember, I said that when you look at or the growth rate of, let's say, seagrass ecosystem, it's usually very, very high. And that applies also to mangrove ecosystem and salt marshes. However, while it may look like it's just another turnover of this ecosystem, there is so much accumulation of carbon during growth. When there is a death of the above ground biomass, most of this carbon is actually stored over time. And therefore, that is what contributes to this huge below ground biomass, or rather sediment rich carbon within the soil compartment. So of the carbon stored within these three ecosystems, I mentioned also that most of this carbon is actually stored within the soil compartment. And some of them, especially the seagrass ecosystem and the salt marshes, stores up to 99% of their total carbon within the soil compartment. So when you look at the first 1 meter of these three ecosystems, that's where most of the carbon is actually stored. Beyond that, usually there is very minimal accumulation, and rather minimal carbon stored below that. And therefore, even when we try to estimate the amount of carbon that is stored within a given ecosystem, most of the time, be it seagrass or mangrove ecosystem, we actually measure the carbon up to only 1 meter, because that's where most of the carbon is actually stored. So recent studies estimates that carbon storage in the first the coastal and marine ecosystem is estimated to be approximately 280 megagrams of carbon per hectare for mangroves, followed very closely by the salt tidal marshes, which stores approximately 250 megagram carbon per hectare. And while seagrass stores half of what mangrove stores within 1 meter 1 meter length from the sediment. And therefore, when you look at those three ecosystems, mangroves happen to be the most, have the highest potential for carbon sequestration, followed closely by tidal marshes and, of course, the seagrass ecosystem. But that does not mean that seagrass are less important. And when you still compare that with most of the tropical ecosystem, you will notice, or you'll appreciate that most seagrass are way much have bigger potential as compared to the tropical other tropical ecosystems. And therefore, in the recent past, here, especially here in Kenya, there has been attempts to try and combine the mangroves and the seagrass ecosystem in terms of trying to offset the carbon. And a classical example is a project that we have in South Coast of Kenya, where in Gazi Bay, where they have used mangrove as a carbon offset project. And I remember I shared a clip of that. And beyond that, due to the success that that has offered, they have now gone a step further and tried to couple seagrass ecosystem, such that they are combining both mangrove ecosystem and seagrass ecosystem because of their interconnectivity, and therefore they use that to offset and sell their carbon based on those two major ecosystems. So in order to be able to estimate how much carbon is being stored in these ecosystems, it's always good to use emission factors. And the emission factors that are used are based on the conversion factor of CO2. So we use a conversion factor of 3.67, which is usually based on the molecular weight of the CO2. So for example, the molecular weight of CO2 is a V carbon is 44 divided by 12, which gives us 3.67. And therefore, that is what we use in converting carbon or stock into an equivalent CO2. So when we destroy 1 hectare of forest, how much carbon is emitted in the atmosphere? Or when you conserve 1 hectare of mangroves against conversion, against any form of destruction, how much carbon are we keeping in safe? So if you convert, if 1 hectare is, there is be so much carbon released in the atmosphere. When you conserve 1 hectare of mangrove, there will be so much carbon stored within that ecosystem. So, and therefore, this is what gives us the carbon dioxide equivalence. So carbon in the first calculated approximately as 1,030 megagram carbon CO2 equivalent per hectare for most of the healthy mangrove ecosystems. So how do you arrive at 1,030 megagram CO2 equivalent per hectare? You use these first tier estimates. 280 multiplied by 3.67 should give us 1030. If you multiply 250 for tidal marshes, multiplied by conversion factor for CO2, which is 3.67, it should give you 920. If you use 140 for seagrass ecosystem and you use the conversion factor of 3.6, it should give you 520. That is what you will have below 1 meter sediment. So that is besides the amount of carbon that is stored in the leaves, in the branches, and in the live below ground biomass, or the roots, if you will. This is just what is in the soil. So when you add the vegetative part of the carbon, be it seagrass, be it mangroves. So in the case of mangroves, it will give us around 1494. For salt marshes, it will be 950, and for seagrass ecosystem, it will be 607. So when you look at that in terms of how much it's adding, you will notice that mangroves, of course, adds approximately close to 500 megagrams carbon, meaning it has very huge amount of carbon still within the above ground biomass as well as below ground biomass. But when you look at how much is being added from 920 to 950, you will notice that it is very, very minute. And therefore, what we really want to underscore here is that most of the carbon, particularly for seagrass and salt marshes, it's actually in the soil. And that's why I was saying almost 99% of all the carbon that we attempt to conserve within these ecosystems is usually within the sediment. And therefore, the vegetative part of that ecosystem, of course, accumulates very small amount of carbon. But due to the high turnover rate, there is a very high growth rate of seagrass. There is high growth rate of salt marshes. There tends to be accumulation of that, because every time there is growth and death, all whatever is actually dying is not decomposing, and therefore it keeps accumulating and forming a huge mat of carbon that is stored within those ecosystems, and therefore they require to be protected at all cost. And or if you will, we need to restore the degraded areas so that they can continue to contribute to carbon sequestration. So when you again look at the mean carbon storage above and below ground in all the three coastal and marine ecosystem vis-a-vis the tropical rainforest, what you will notice that the area that is marked in dark blue is the soil organic carbon, and the amount that is stored is depicted by light blue. That is the living biomass. So what I really want you to see here is that when you look at the boreal forest, you can actually see that it's almost half of the carbon because when you look at these two ecosystems, the boreal forest and the tropical rainforest, these are ecosystems that are characterized by very high aerobic soils, and therefore there is very high decomposition taking place, and therefore whatever accumulates in the sediment or in the soil tends to be released back in the atmosphere, and therefore most of what remains is the living biomass. That is what accounts for most of the carbon. Unlike the coastal and marine ecosystem, which are characterized by the anaerobic sediment, and therefore most of what accumulates below the soil is usually stored as carbon, and there is very minimal release of CO2 back in the atmosphere because most of it does not decompose, and therefore there is high accumulation of that carbon over time, and that's why these ecosystems are considered to be very, very critical in as far as carbon sequestration is concerned. So when you compare coastal and marine ecosystem compared to other ecosystems, you will appreciate that the coastal and marine ecosystem tend to release significant amount of CO2 per unit area upon conversion or degradation. So, and therefore that is why there is need to conserve this ecosystem, or there is need to invest in restoring this critical ecosystem because of their potential in storing carbon. So large stores of carbon in the soil of these three ecosystems are exposed or released in as CO2 into the atmosphere when they are degraded or converted through maybe deforestation and logging and that kind of a thing. So, although the combined global area of these three ecosystems is only ranges between 2 to 6% of the total area compared to tropical rainforest, the degradation of this key coastal and marine ecosystem account up to 19% of the carbon emission. What that basically tells us is that they have very high potential rate, and therefore there is need to conserve them at all costs, because there is no comparison between tropical rainforests that are considered to be very important ecosystem vis-a-vis the coastal and marine ecosystem, particularly mangroves, seagrass, and the tidal marshes. So when you look at the estimates of carbon released by land use change, if we were to change the area under mangroves or the area under seagrass to coastal ecosystem, when you compare them, you look at them globally. So, for example, when you look at mangroves, the global area extent is approximately 15 million hectares. So these are million hectares. So we have around 15 million hectares as the coverage under mangroves. So, according to the estimates that have been done, the current conversion rate per year is approximately 2%. Every year we are converting the total area extent of mangroves of 2% back to other land uses, maybe due to coastal development and other pressures. And what that basically means is that we are converting around 300 hectares per year back to other forms. That is almost equivalent to almost 800 hectares per day of mangroves being converted every single day back to other land uses. So, and when that happens, what that means is that we are releasing more than 900, almost 1,000 megagram CO2 equivalent per hectare back to the atmosphere. So the mean estimate, when we combine all the three ecosystems, mangroves, tidal marshes, and the seagrass ecosystem, the mean estimate carbon emission from the loss of all these three ecosystems is equivalent to 0.45 pentagrams. And a pentagram is actually equivalent to 1 billion metric tons of CO2 being converted back to CO2 every year. So that is the numbers. You may think that those numbers are small, but this is equivalent to fossil fuel CO2 emission, equivalent to what the entire United Kingdom, which is a developed country, is emitting back to the atmosphere. So whatever we are converting, when you are converting this three ecosystem back to other land uses, it's equivalent to what the entire country, the entire United Kingdom is actually contributing in terms of CO2 emission to the atmosphere. And therefore, we have to protect this coastal and marine ecosystem in as far as climate change is concerned at all costs. So basically what this map is showing, it's basically showing the global distribution of the blue carbon ecosystem. So if you remember very well, most of the three ecosystems basically mirror each other, because most of these ecosystems are most dominant and has the highest extent and more complex within the tropical region. So the coastal and marine ecosystem are basically found along the coastal of every continent except the Antarctica. But what you will notice from this is that they are most common around the tropical region. So there are quite a number of activities that are contributing to this conversion, to this degradation of our coastal and marine ecosystem. And key among them include the aquaculture, is contributing in a big way to conversion of this ecosystem. Agriculture, over exploitation of the ecosystem, particularly the mangrove ecosystem for poles, industrial and urban development, as well as pollution. All these are contributing to conversion of these three major ecosystems to other forms. And by extension, this is contributing to loss of, to release of CO2 in the atmosphere. So this drivers of conversion as a result of climate change. Ask ourselves is conservation and restoration of coastal and marine ecosystem a solution to reducing atmospheric carbon? Is it a solution? Yes, it is. Potential income, when you look at it in the monetary terms, in terms of money that is being generated by converting this ecosystem to those other uses, vis-a-vis conserving this ecosystem and maintaining their integrity, there is no comparison. So the potential income generated by converting this three ecosystem for carbon storage through maybe avoided emission, ensuring that those ecosystems are protected, or sequestration potential is comparable to or even exceed the potential income, or if you will, or what we call the opportunity cost of some of the more common causes of conversion or degradation of the coastal and marine ecosystem. So if we were to convert all the mangrove areas to crops or to fish ponds or to any other forms, and then we look at the value, the monetary value of doing that, how much are we deriving from that conversion? Then there is no comparison. It's the potential that we can have, the potential that we have in terms of even maybe selling carbon credit is much better than converting a hectare of mangroves back for aquaculture and or any other form of conversion. So coastal and marine ecosystem are highly valuable for their provision of other ecosystem services, including fishery habitat, prevention of coastal erosion, water filtration against other ecosystems like coral reef and seagrass, and protection from climate change related storms and the like. All these are the other most very important services that are provided by this ecosystem over and above the carbon credit that you can actually get from conserving these ecosystems. So, but the big question is there, or rather, are there established methods or methodologies of measuring or monitoring carbon sequestration, storage, or emission from these coastal and marine ecosystem? Are there established methods that we can use to estimate how much carbon is stored by our Kenyan mangroves or by our seagrass within the territory of Kenya? So currently, there are a number of robust methods that reliably used to measure and monitor carbon stored in the vegetative biomass as well as the soil of the coastal and marine ecosystem. So we have an established methods. So there is a detailed field guide And if you will, you can actually download this, or you can look at this titled Methods for Assessing Carbon Stocks and Emission Factors in Mangroves, Tidal Marshes, and Seagrass. This is a document that has been published, and therefore it's possible to know, to use such a guide to know how much does our mangrove, what is the potential of our mangroves within the territory of Kenya have in terms of carbon storage. We can actually use that, use the emission factors that are there, and the assessment and the assessment method that have been proposed. So such standardized method allow consistent collection of comparable data around the world, and therefore it's possible to compare the potential in Kenya vis-a-vis Tanzania, the potential in Kenya vis-a-vis Madagascar, or potential in Kenya vis-a-vis any other area, while also being consistent with the international standards, such as the those related to guidelines of IPPC. So the IPPC, which stands for Intergovernmental Panel on Climate Change, they use these standards to estimate how much potential, what is the country doing, what is each country doing to ensure that they are maintaining the effect of climate change. So in the recent past, as recent as 2013, there was IPPC developed supplementary guidelines that focused on the coastal and marine ecosystem for greenhouse gas inventory, including all the wetlands, including the mangroves. So it is scientifically well established that coastal and marine ecosystems are important carbon sinks, and therefore they have come up with these guidelines on how to estimate the amount of carbon that these ecosystems store within those ecosystems. So there are various methods that have been used to estimate the amount of carbon that we have in each of these ecosystems. So the estimation of carbon stock are organized into three hierarchical tiers. So there are three levels at which you can actually estimate the amount of carbon you have in a given ecosystem. So the first tier is what you call tier 1 estimates. This is how you estimate the amount of carbon based on the IPPC default values. You remember the values I was giving about on mangroves, how much, what is the potential of mangroves in terms of carbon storage per hectare. So that is tier 1 estimates. They are based on tier 1 estimates because they are generalized for all ecosystems. In terms of accuracy, tier 1 estimates have the least accuracy and certainty, but they are better in a situation where you don't have a more accurate estimates. Are we together up to there? Hello?
Yes.
Yes.
Are you people following?
Yes.
So then we have what we call tier 2 carbon stock estimates. So tier 2 carbon estimates are based on regional or country specific values. So when you look at tier 1, it's a more generalized default figure or default values. For example, for the case of mangroves, we were talking about 386, something, a figure close to that. While for seagrass, it's around 180. And for salt marshes, it's around 250. So that is a more generalized default value. But is the potential of mangroves in terms of carbon storage. Is it the same across the globe? I'm asking you a question. Is the potential of mangroves in Kenya the same as those of Indonesia, for example? Hello?
Not really.
So where do you expect to have very high values, and why? Hello. Where do you expect to have higher values when you compare, for example, Kenya and Indonesia?
In Indonesia,
You'll expect to have high carbon stocks of mangroves in Indonesia. Is that true?
yes.
So why is that the case?
Kenyan's mangroves are degraded. They're
Is it
polluted.
just, what do you mean? Is that the reason why you think?
And the cover, the cover of mangrove forest in Indonesia is larger as compared to Kenya.
We are not looking at the area extent. We are looking at per unit area, per hectare. When you compare the potential of mangroves in Kenya per hectare, will it be the same as that of Indonesia per hectare? Who was that engaging with me?
It was Clifford Awino.
Yeah, but Clifford,
Yes.
you don't disappear. You don't disappear. You keep on so that you get to understand what I mean. I know whether you actually understand what we are trying. The point I'm trying to drive home. So I was asking, you have 1 hectare of mangroves in Kenya, and you have 1 hectare of mangroves in Indonesia. Will they have the same potential? Or any other part? Will they have the same potential?
Yes.
Do you people agree with Clifford that they have the same potential?
I don't think they have the same potential.
Who is that?
Because
That's Mike?
yeah,
Mm-hmm.
I don't think they have the same potential because how the nation of Indonesia, based on their values and some of the things they hold dear, is the forest aspect, the natural aspects of their land. And in Kenya, it's not as highly valued and taken into that much account, even by the budgetary sector, or let's say the treasury, or most conservation aspects. They are lightly esteemed in our country.
Putting that aside, when you look at the complexity of these ecosystems, even within Kenya itself, when you compare Kenya and Indonesia, Indonesia is actually in the tropical region where we have the most complex ecosystems. So in terms of complexity and structural complexity, forests within the Indonesia region will be more complex as compared to the Kenyan forests. Putting aside those other dynamics. So when you look at a tropical rainforest, or not really, generally the forest within the tropical region, and those that are in the areas that are known to be very dry, or in the in the northern, or rather those that are in the Middle East, you'll notice that the forest within the Middle East region will be more standard than a forest within a tropical region, because meaning it will be more complex in terms of structure. It will have bigger trees and a more healthier ecosystem, and therefore that's what I was trying to drive home, that a forest in Indonesia, for example, will be very different from a forest in the Middle East, because a forest in the Middle East will be a dwarf in nature, or rather in terms of structure. And therefore, when you compare those two forests, one will have lesser potential in terms of carbon storage as compared to the other. And therefore, when we talk of Tier 1 and Tier 2, Tier 1 is more generalized, irrespective of where that forest is, be it in Middle East, or be it in the Indonesia or in Kenya. We are talking about using more or less the same figures in as far as IPPC is concerned. But when it comes to Tier 2, it becomes now more specific. That in Kenya, Tier 2, for example, are estimates that are based on regional. It could be values or figures that we have for example, Western Indian Ocean. It will be different from a tropical forest we have in Indonesia or in Philippines. Then, or it could be, we have values for Kenya and we have values for Madagascar or for Tanzania. So they'll be more accurate and more specific as compared to Tier 1. And therefore, in terms of accuracy, they are more reliable. In terms of resolution, they are more reliable as compared to Tier 1. On the other hand, we said we have 3 levels or hierarchical tiers. So the Tier 3 are based on estimates that are based on a country or forest specific. And I would like to give an example here again. When you look at the Kenyan mangrove forests, the mangrove forest we have in Lamu are more complex structurally as compared to those in South Coast. So, and therefore, the potential of the mangroves of, let's say, Lamu, which are more, they are riverine and more pristine, they'll have higher potential as compared to a mangrove that is subjected to a lot of it's not riverine in nature, and it's also subjected to a lot of stresses, and therefore the potential, the sequestration potential for Lamu mangroves is much higher as compared to that of South Coast, and therefore this is a Tier 3 estimation. So if we were to do estimation based on, we do that assessment of mangroves in Lamu, and we do a data assessment of mangroves in South Coast, then we have a Tier 3 estimation, meaning they are highly specific. It's a highly specific figure for South Coast, and we may also have a very specific figure for the mangroves of Lamu, and that is what we are referring as Tier 3. So there are those 3 levels. So if we do not have if we have not done any research, for example, in Kenya, in as far as carbon stock is concerned, we use Tier 1, or we use Tier 2 if we have a regional estimate, for example, for the Western Indian Ocean, or we use Tier 3 if we are very particular when it comes to carbon sequestration. So when it comes to carbon offset project, it's always advisable to use Tier 3 estimation of the carbon stock, so that we are very specific about the values that you are using. We are not just using default values. You only use default values when we have no better figures to use. And therefore, when you look at the global blue carbon stocks, when Tier 2 and Tier 3 estimates are not possible, Tier 1 estimate can be used. So, for example, the mean and the range value of soil organic carbon stocks for 1 meter depth of most of for all the 3 coastal and marine ecosystems. In the case of mangroves, the value that is used in terms of carbon stock is 386 megagram per hectare. For salt marshes, the default Tier 1 values that is used across the globe is 255. For seagrass ecosystem, the Tier 1 values that are being used for estimation of the potential of seagrass ecosystem is 108 megagram per hectare. So when you have the values that you have there, those are Tier 1 values according to the IPPC guideline. So that's what we use for those 3 ecosystems. So the range, of course, is very huge depending on the health of different ecosystems that were used to come up with this average. This is the average, but this is the range. We have some that are very degraded, and therefore the potential is very low. And we also have some that are very healthy, and therefore the potential is very high. But the average is 386. So when you use the average value, and you combine both the below ground biomass and above ground biomass and soil, then you end up with 1415. How you end up with this figure is that you multiply this by 3.67, which is the conversion factor value for CO2 equivalents. And that applies again for salt marshes and applies for the seagrass ecosystem. So these numbers, they are based on globally average carbon stock estimate according to the current literature that is captured in the IPPC guideline. So if we use the Tier 1 assessment of carbon stock, this is achieved by basically multiplying the area of an ecosystem by the mean carbon stock, which is, in this case, for the mangroves is 386 for that ecosystem type. For example, you may ask yourself, how much carbon is going to be stored in the biomass and top 1 meter of soil, 567 hectares of mangroves in a given site. So this one, how you go about this is that you will take the total carbon per hectare. That is, it's already known that for mangroves, it's 386. Then you will multiply by the area of the mangroves under mangrove, which is 564 hectares. So that will give you Tier 1 total carbon stock for that area. So if you want to convert, if you want to estimate and know if we restore 1 hectare of mangroves, then this is the amount of carbon that we expect to conserve or not to release in the atmosphere. Or alternatively, if you will, if we were to degrade 1 hectare or 556 hectares of mangroves, how much CO2 are we likely to release back in the atmosphere? So it's this, you have the value, the number of hectares you have here multiplied by the tier 1 estimate, which is 396, then multiplied by the conversion factor, which is 3.67. So in this case, where the total carbon equals the mean carbon stock for a given ecosystem, while the area is the area of the ecosystem being investigated. So in this case, I said it's 386 multiplied by 564, which will give us 700 megagram of blue carbon in the study area. But when, again, you need to use the conversion factor. If this carbon is released, if we expose this carbon, how much CO2 are we going to release in the atmosphere because of that conversion? Then you multiply by 3.67. And that will give us almost 800 megagram equivalents of CO2 being released back in the atmosphere. So I want us to look at this. This is the aerial coverage of mangroves in Kenya for the different counties. So the area under mangrove in Lamu is 36,350 hectares. The area that is degraded within within Lamu is 14,407. The same applies to Tana River County, the Kilifi County, Mombasa County, and the like. And the total area under mangroves in Kenya is approximately 61,300 hectares of mangroves. However, 40% of all the mangroves in Kenya are degraded if we were to combine and do an average across the 5 counties. So I want us to have a break. And as you have a break, I want you to calculate for me. If we were, for each of the counties, I want you to use the degraded mangrove areas and estimate for me, how much potential of CO2 we are likely to release or to conserve if we were to restore the entire 38% of Lamu, 36% of Lamu, 40% of Lamu, 49% of Mombasa, and 45% of Kwale, because those are the degraded. These are the degraded areas. So what will be the equivalent CO2 that we are likely to conserve or to avoid releasing in the atmosphere if we were to restore these sites? Have you understood the assignment? Hello?
We are absorbing.
Yeah?
We are still absorbing, like we've not
What I'm asking,
clearly understood it.
you have understood that if we lost 1 hectare of mangroves, in this case, if we were to lose 500 of mangroves, then the amount of carbon that we are likely to release into the atmosphere is this amount of CO2. So in the case of, this is the scenario in Kenya currently. The area under mangrove is what we have under here. And this is the degraded area under mangrove, and this is the percentage. If you were to do that. So I want you to use the numbers that you have here, assuming that these areas were completely degraded, and they have been converted back to mangrove, healthy mangrove through restoration. So how much carbon are we likely to avoid releasing in the atmosphere for each of the 5 counties? Have you understood?
Yes.
So can we have a break of 10 minutes, and I want you to come back with figures for each of the counties. Okay. So we'll be back in 3:32, and I want us, when you come back, you must have CO2 equivalents of restoring the degraded mangrove areas in Kenya. Kuna swali? Kama hakuna, we break and get the figures by the time you're coming back. Hello. Have you guys converted the areas that are degraded? What is the potential CO2 loss? Maybe I'll begin with individual. Nancy Musiera. Nancy? Hello? Nancy? Maureen?
Yes.
So have you tried to convert, for example, the area under Lamu that is degraded?
Yes, I tried to convert
With that
and found it 20 million cubic, uh, 20 million megagrams of carbon.
will be?
Will be that have been lost, so it will be conserved if the area was restored.
Okay. And that's correct. Or if we lost, if we don't or rather if we were to restore, or if we were to consider if we have lost that extent of area, then it would mean, using Tier 1 estimate, then it would mean that we'll have lost, we'll have emitted to the atmosphere an equivalent of 20.5 or 20.4 megagram, 20.4 million megagrams of CO2 equivalent, all right? Not carbon, CO2 equivalents, all right?
Yes.
Has everyone put in that?
Yes.
So, Mbudia, what would be the CO2 loss in Tana River?
1.6 million.
Sorry?
1.6 million. I would say this is a carbon equivalent, CO2 equivalent restored.
So, to the atmosphere by not restoring the degraded area in Tana River. So, Mike, what about in Kilifi? Mike? David?
Philip, it will be 4.8 million megagrams per hectare of CO2 equivalent.
Megagram
Huh?
CO2 equivalent. Yeah?
Yeah, CO2 equivalent.
Okay, excellent. Who else is on board?
Sada.
Faith? Faith? You know, I notice some people just leave their gadgets and disappear. Yeah? Like Nancy. Nancy, why is Nancy on board? Is Nancy with us? Kenga? Kenga,
Yes.
are you with us?
Yeah, I'm with you.
Yeah, so in your calculation, did you do calculation for any of
Yes, I did.
what would be the equivalence for after Kilifi? After Kilifi is what? For Mombasa? For Mombasa County, how much shall we have lost?
$2.6 million
Of what?
of carbon.
No, you're not saying it right.
2.6 megagrams of carbon.
2.6 million
Million megagrams.
of CO2 equivalent, not just carbon. You see, carbon is different from CO2. That's why you need to use a conversion factor of 3.6 so that you call it CO2 equivalence. That's the CO2 that will have released back in the atmosphere. Okay?
Yeah.
Then lastly, we have for Kwale County, Clifford.
5.2 million megagrams CO2 equivalents.
Okay, so I can see you got it right, all of you. So I now hope that you understand the